Hey everyone, in this video, I'm going to walk through the steps I took to improve the performance of my stroke classification model, how I validate it, and also what works best. Let's dive in. For the improving model performance, the first thing I focused on was feature engineering because good features lead to better predictions. Here are some key improvements I made. For the feature interactions, I created a new feature called BMI age interaction by multiplying the BMI and age. This helped capture how weight and age together affected the stroke risk. And the second one is the Binning continuous variable. Instead of treating age as a single continuous variable, I grouped it into age categories like young, middle age, and also elderly. This helped to model detect age-based stroke risk better. And also for the when hot encoding for categorical data, I transform work type, residence type, and smoking status into numerical values using when hot encoding instead of label encoding. This prevents the model from assuming an order where there was none. This changes alone boosted my logistic regression AUC from 0.79 to 0.81. And also for the model comparison, the strengths and weakness, I compare three models based on their F1 score and also business impact. And for the logistic regression, the pro said that it is really simple, interpretable, and also works well with limited data. However, for the cons, it's like struggling with nonlinear relationships and also lower accuracy. For the random forest, the pro said that it can handle the missing data well, less overfitting than single decision trees. However, the con said that it's still prone to overfitting, hard to interpret. And also for the XGBoost, its pro is that it can just have the best performance, handle imbalanced data well. However, for the cons, it's like it needs more careful hyperparameter tuning. For the final choice, I used the XGBoost with an ensemble of all three models to improve overall stability. And for the handling class imbalance, since the stroke cases are just much rare than non-stroke cases, I had to deal with class imbalance. And I tried about like three methods. The first method is about the SMOT method. This generates the synthetic stroke cases to balance the data set. But too much SMOT cause overfitting. So I sent sample strategies 0.6 instead of 1.0. And also for the class weighting, I adjusted class weights, so the model paid more attention to the stroke cases. This was especially useful in logistic regression. And also, instead of using the default of a 0.5 probability threshold, I optimized it using the ROC curves. And this improves recall while keeping precision reasonable. This reduces the force negative and boosted my F1 score on the leaderboard. And also for the hyperparameter tuning and validation, tuning hyperparameters made a big difference. Here's what I did. The random forest, it is just like limited max steps to 7 and increase minimum sample split equal to 0 to prevent overfitting. And also for the XGBoost, adjusted learning rate equal 0.05, added L1 divided by L2 regularization. And fine tuning max steps is about like equal to 0. For validation, I move from a simple training test split to fivefold cross validation, which stabilized my performance. And also, I just also check for the overfitting. I plotted a learning curve to check if my model was overfitting. If training accuracy is high, but validation accuracy is low, the model is overfitting. If both train and validation accuracy are low, it's just underfitting. To fix this, I reduced the tree depths in the XGBoost and applied dropout in neural networks. And also for the confusion matrix and business implication. Finally, let's talk about the confusion matrix and precision recall trade-off. For the false positive, predicting stroke when there's none, wasting the medical resources, and for the false negative, missing a real stroke cases, much worse, because patient did not just like get early treatment. I decided to lower my decision threshold slightly to reduce the false negative and also prioritizing the patient safety over perfect accuracy. And also for the final results and takeaway, with all these improvements, my final model just ranked a little bit higher on the leaderboard. Featuring engineering made my model learn better patterns. Hyperparameter tuning boosted the generalizations. And also the class imbalance handling the reduced force negative. And the cross-validation stabilized performance. If I had more time, I will explore more on the models and also explore more on the classification for further gainings. That's it for my stroke classification project. And thanks for watching.